Claeys will, from Louvain, of course, will talk us about the KPZ equation.
Thanks a lot. Thanks a lot for the invitation and the organization also of this very nice conference. So yes, in my talk we will indeed see some things that we've seen appearing earlier today and yesterday also. But okay, nevertheless, I will start from the very beginning. So the model or the problem that I will be considering is related to the what is called the KPZ equation and certain asymptotics for the solution of this equation. So what is the KPZ equation? It's an equation that has been introduced more than 30 years ago by Kardar-Parisi-Zhang as a model for growth of certain surfaces. And so this is the equation. It's a quite complicated equation, especially because it's a stochastic equation. So here's a stochastic term. So h is a function of x and t. So x and t, although I denote them by capitals, but they represent time and space. And so there's a time derivative, there's a second space derivative, and there's a square of the space derivative. And then there's a random term here, which is called, or which is space-time white noise. It's not so important to understand precisely what this term means. It's enough if you know that this is a random term in the equation. If you want to interpret this physically in terms of growth of surfaces, then this is somehow a velocity term, which describes the speed at which a height function evolves. And this is sort of can be interpreted physically as a term which represents surface tension. So this stochastic PDE allows to model various types of growth of certain surfaces. And so I have a couple of pictures which are from a paper of Jeremy Quastel. So for instance, if you burn a sheet of paper, the evolution of the burning front can be modeled by this equation. Also, there's something particular about coffee stains. I don't know if you know this, but apparently, well, there's a difference between coffee and most other liquids, which is that coffee contains much more round particles than most other liquids, which contain more elliptic particles. And a physical consequence of this is that if you have a stain of coffee, and if you let it dry out, then what you will see, most of us experienced it, you will see on your sheet of paper, when it's dry, you will see only a ring at the edge of the coffee stain. With most other liquids, this is not the case. You will see just the stain completely. But with coffee, and it is apparently because this amount of round particles that all the particles, or most of the particles, go to the edge, and they create some ring. And this ring can also be modeled by KPZ. This has been described in quite some mathematical detail. Then there are some more serious applications in bacterial growth, but where there's somewhat less mathematical evidence of that it's a good model for it, and also it could be a model for growth of certain tumors, although that hasn't really been understood. Okay, so the solution theory of the KPZ equation is quite complicated. It's a stochastic PDE, so it's not so clear what it means to be a solution of this equation. And the classical way to give a mathematically rigorous meaning to it is by going through the Kohl-Hopf transformation. So you write the solution h as the logarithm of some function z. And this Kohl-Hopf transformation relates the KPZ equation to the stochastic heat equation. This you can just do explicitly. If you formally substitute h of this form, then you will find that z has to satisfy this equation, which is a stochastic heat equation. And so this was observed by Bertini and Giacomin. And so for this equation, the solution theory is, I would say, classical in the sense that you can define solutions through either stochastic calculus methods, which is still not maybe not very classical, but in the theory of stochastic differential equations, it's a much more classical equation than KPZ, for which these methods don't work directly. So yeah, more recently, and I won't use this, but there's famous work of Heirer, who gave also a rigorous meaning to what it means to be a solution of the KPZ equation, but without passing through the stochastic heat equation. There are several. There are in fact three classes, I believe. Well, maybe more, but three, which are the most prominent classes of initial data, which are the solutions that appear in applications. And one of those solutions is the one that I will study today. Is what is called in the physics literature the solution with narrow wedge initial data. What does this mean? So it means that you solve the stochastic heat equation with delta function initial data. That's what it means. What it means for the solution of the KPZ equation, there's not really a formal statement of what it means for the initial data. It's a logarithm of a delta function, whatever that may mean. But what you see as time goes to 0 is that you see roughly, it's a stochastic function, so it can be anything, but typically you see the shape of a parabola, which get more and more narrow as time decreases. And so that's why it's called narrow wedge initial data. Okay, so that's the solution that I will talk about for the rest of this talk. Now, there's one very important thing to notice, that is that so here you see this parabola-shaped typical shape of the solution. So typically you have minus x squared over 2t. And so in fact, the probability distribution, if you scale things in a good way, the probability distribution of the solution doesn't depend on the space variable x. This random variable has a distribution which is independent of x. So it means that we can just look at h of t and x equal to 0, and we can look at this, and this will tell us everything what we want to know, as long as we study single x fluctuations of the solution. Moreover, so if we want to study asymptotics, especially for large time asymptotics, it's convenient to scale the solution in a certain way. And okay, we take h at time 2t. This is not so important, but okay, it's a normalization that appears quite often in the literature. So it's just you add this t over 12 to h, and you divide it by its typical size. So this random variable epsilon t is now what I will study. So what do we want to know? We want to, also in view of these applications, we want to we want to say something about the probability distribution of this random variable epsilon t. We won't be able to find some explicit expression for this distribution. So in a sense, the best we can hope to do is to have control over the tails of this probability distribution. Also, in view of the applications, if you think of a burning front, you would like to be able to predict at a certain time in the future what is a safe region on your sheet of paper where the burning front hasn't arrived yet. So this is the type of things you can describe with these tails of the probability distribution. Okay, So this was the classical description of the KPZ equation and this special narrow wedge solution to it. Now the more recent evolutions, they started in 2010, I would say, when Amir, Corwin, and Ghosal, they found an exact expression for the Laplace transform of the stochastic heat equation solution. So this also characterizes exactly the solution of the KPZ equation, or the probability distribution of the solution. And more precisely, they relate it to a certain multiplicative statistic in the Airy point process. I will explain what this is later. Or equivalently, it can be written as a certain Fredholm determinant. And so these results in around 2010, there was quite some activity around 2010, 2012, 2011. So almost the same results had been derived by Sasamoto and Spohn, which was also, most of their analysis was also rigorous, but there were some parts in the analysis that they didn't do completely rigorously. And then in the physics literature, there were also Dotsenko, Calabrese, Ledoussal, Rosso, who predicted or confirmed the same results. And in fact, these exact expressions for the Laplace transform, deriving them relied on a relation with asymmetric exclusion processes. They can be seen as a discrete approximation of the KPZ equation. And so Tracy and Widom, they obtained in 2008, I think, they obtained similar exact expressions for the height function in these processes, and this was used to derive this relation with the Airy point process. So let me try to explain to you this result of Amir, Corwin, Ghosal in more detail. So for that, I first need to introduce the Airy point process. So there's a lot of things to say about the Airy point process. I will try just to explain you the essential things that you need to remember, hopefully, for the rest of the talk. So the Airy point process, it's a point process on the real line, which means that it's a probability distribution on configurations of particles. Moreover, what is very special for this point process is that it's a determinantal point process. This means that all correlation functions of the particles, they can be expressed as a determinant of a certain correlation kernel, which is this kernel, which is expressed in terms of the Airy function, two equivalent ways. And so, in fact, all the properties of this Airy point process, they are encoded in this function of two variables. There are two, I would say, probabilistic properties of configurations in the Airy point process. Almost surely there are an infinite number of points on the real line, and almost surely there is a largest particle. Okay? And there are many applications of this Airy point process, but one of the most known appearances of this Airy point process is that it models typically largest eigenvalues of random matrices near soft edges. For instance, in the Gaussian unitary ensemble, or for Wigner matrices and many other models of in random matrix theory. Also models in statistical physics, but I won't go into detail there. Okay, so this is the Airy point process. So what's now the result of Amir? Well, it's not really the result of Amir, Corwin, and Ghosal. So they wrote it slightly differently. Borodin and Gorin in 2016. They used the results of Amir, Corwin, Ghosal, but they formulated them in a more convenient way, at least for us. So they looked at this average of a double exponential of our random variable epsilon t. So this is indeed, this is the Laplace transform of a rescaled version of the solution to the stochastic heat equation. And so this Laplace transform, so this is expectation with respect to the white noise term in the KPZ equation. It's equal to an expectation in the Airy point process, and it's a multiplicative expectation. So you take a product over all points in the Airy point process, and you take the product of these vectors, which depend on the position of the particle zeta j. So the zeta j's, they are the particles, the points in the Airy point process, and you take this product, this infinite product. So this expectation is it's a well-defined quantity. It's a finite number which will depend on t and on s. And yes, so an interesting interpretation of this expectation. You need to look a bit closer at this to see it, but you can, if you think of a configuration in the Airy point process, and you're going to thin this process by removing each particle independently with this probability, which depends on the position of the particle, but you thin each particle independently with this probability. I will call this the thinned Airy process. Well, this Q of St is the probability that the thinned Airy process is empty. So the Airy point process itself has an infinite number of particles, but after this thinning procedure, it could be, there could be some particles remaining, either an infinite number, finite number, or none at all. And so this Q of St is a probability that there are no particles at all in this thinned Airy point process. You can see it by, okay, essentially it's just looking a bit at this thing and noticing that the probability of an event is the expectation of the indicator of this event. But you have to be a bit careful because you have two different expectations, one with respect to the Airy point process and one with respect to this thinning procedure. But it's elementary to see that it's the same. Okay, so this function Q of St, which is this Laplace transform of the solution to the stochastic heat equation, this is an important object that we will study now. Okay, so now it's a general property of a determinantal point process that any multiplicative statistic, you can write it as a Fredholm determinant. And so in this case, applying this general property, our function Q of St, it can be written as a determinant of an operator, which is the multiplication of a multiplication operator with the integral operator associated to the Airy kernel. And this function sigma, it's this function. So sigma is the precise form of sigma is not so important, but it's a function, it's a probability distribution function, so it tends to 0 exponentially fast at minus infinity, and then it goes exponentially fast to 1 at plus infinity, and the associated density sigma prime is symmetric. Okay. Okay, now many of the, so this choice of sigma comes in fact from the result of Amir, Corwin, Ghosal, and it's this specific choice of sigma that relates to the KPZ equation. Now, many of the things that I will say from now on, they will hold for more general class of functions sigma, as long as they tend to 0 sufficiently rapidly at infinity and they remain bounded at plus infinity. But also some of the things that I will say will rely on this specific form. But yeah, I will come back to this later. Okay, so this is, yeah, it's some Fredholm determinant related to the Airy kernel operator. Now you can use some elementary properties of Fredholm determinants to write this Fredholm determinant in a different way. You can also write it as a determinant of an integral operator corresponding, acting on minus s infinity, corresponding to this kernel. Now, what can we say about this this kernel? Several things. The first thing is that this is a kernel that also appears in models of finite temperature free fermions. In random matrix theory, these are models called MNS matrix model or grand canonical ensemble sometimes. And the second thing to notice is that when t gets large, it means that the variable of sigma will become a rapidly changing variable, and it will mean that this sigma approximates a step function, which is so this, if I evaluate this at t 1/3 r, then my function here will become steeper, and for large t this will approximate a step function. And so you can see fairly easily that if t goes to infinity, this approximates 1 for positive values and 0 for negative values, and then this converges to the integral representation for the standard Airy kernel, which I showed to you on the previous slide. Okay. Yes, so this is this statement that the limit of this kernel as t goes to infinity is just the Airy kernel. And in that case, Q of st, it converges to the Tracy-Widom distribution, which is the Fredholm determinant of the Airy kernel, acting on minus s infinity, but without multiplication with sigma. This was also proved, I don't know if it was the first proof of these things, but in the paper of Amir, Corwin, Ghosal. So now, so this was this fact that the solution of KPZ can be characterized in an exact way, that apparently this came as a big surprise. It was not clear at all that this would be possible. But now we would like to use this exact characterization of the solution to be able to say, to give some quantitative bounds for the distribution of this random variable. And it seems that the most interesting limit is the limit when s goes to plus infinity. The limit as s goes to minus infinity is also interesting, but it's much easier to analyze, and there more or less everything you would like to know is known. The important thing to know at this point is that Q of st is the Laplace transform of the solution to the stochastic heat equation. And so if we want to understand the tails of the probability distribution, we can use the standard Laplace transform techniques to derive them from asymptotics of Q. So the only thing we need now is good enough asymptotics for Q, and then using just one moment methods for Laplace transforms, we will be able to derive asymptotics for this probability distribution. So the heuristics behind this probability distribution, or behind rather Q of st, it's quite interesting. So the density of the points in the Airy point process, it behaves like a square root when z goes to minus infinity. So if you have the particles in the Airy point process on the real line, if you plot a histogram, this histogram will approximate a square root law if you go far to negative infinity. This is a result by I think it was first derived by Soshnikov around 2000. And so if you know that, then this log of q of st, using the definition of its definition as an expectation of an double exponential of this random variable, you can expect this to behave like the sum of the logarithms of this function evaluated at the points in the Airy point process. And this, heuristically, you can expect it to be approximated by this integral. And this integral you can approximate it for large S and large T by this. Yeah, this requires some work to do this, but it's not so hard to see that this behaves for large S and T in this way, and we have a T 1/3 and an S 5/2. I think these heuristics were first written down by Kryenbrink, Ledoucelle, and Prolak, and this is a quite intuitive picture which allows one to understand what's happening. But the thing is, this approximation that you get from the heuristics, it's not always correct. It's correct when T is not too large compared to S, but if T is large compared to S, then it's not accurate anymore. Yes, there are reasons why this is not valid anymore there, but I won't go into details here. So now let me state our main result. So our main result concerns asymptotics of the logarithm of this function q of st when s goes to infinity. And so if we look at the st plane, so our asymptotics hold for any fixed positive time, but they're also uniform whenever time is not too close to 0, so it's bounded by some small constant, and it cannot go too fast to infinity compared to s. So there's a certain curve like this, t equal to m 3/2 for some arbitrary large constant m. And so our asymptotics are valid if s goes to infinity. T can also go to infinity, but not too fast compared to s. So in this region we will have asymptotics, and they're uniform in this region. So now, what are the asymptotics? Okay, they're a bit complicated, but very explicit. There's this function, which is called the large deviation rate function for KPZ, and which was found first in the physics literature, I believe, by Sazarov, Mearson, and Prolak a couple of years ago. I will come back to their results immediately. It's an explicit function. The only thing that's important for us is that when y goes to infinity, it behaves like a 5/2 power. When y goes to 0, you just have to Taylor expand this. You will see that all those terms cancel out, and you will see that then this behaves like a cubic, like y cubed. So all those terms that are here, they will cancel out with the terms which come from expanding here, and you will get so this is a function that describes a crossover between a 5/2 power law and a cubic law.
So it's not exact, it's more like the function formula.
It's yeah. So this is a function. Yes. So the asymptotics for as y goes to 0 is cubic. As y goes to infinity, it's 5/2 power, and it's something in between that crosses over between those two types of behavior. But this is of course just an exact formula for this this function. Now the asymptotics for log q, and I will immediately after I will explain what was already known and what we add to.
You are not allowed y go to 0 in your formula.
That is true. So y has to remain bounded from below. Yeah, indeed. So yeah, this function, I just wanted to describe this function, but indeed, y going to 0, our results are not uniform in this limit. That's true. Yeah. So this is the leading term, so it's proportional to t squared, and then there's this phi which has to be evaluated at y, which is s times t minus 2/3. We have a next correction term, which is also explicit, and then we have some error terms. It depends how you go to infinity within this region, but there are some log squared terms in S, and then there's some t to the power 1/3. It depends which one will dominate. So these are the asymptotics for the log of Q. So what does this imply for the probability distribution of the KPZ solution? That was what we were after in the first place. And as I said, this can be obtained using classical techniques for Laplace transforms. And the result is, for instance, for finite t, which means we go to infinity just on a horizontal line here, we recover indeed this first term which was predicted from the heuristics. We also get a next term, subleading term, and some error term. So this finite t expansion, so the leading order term was clearly predicted but had never been proved to the best of our knowledge. This finite t expansion, there was no rigorous proof of it. This same expansion holds also when s and t goes to infinity, go both to infinity, but t goes not too fast to infinity, for instance on such a curve. And in that case there were upper and so Corwin and Ghosal last year, they obtained upper and lower bounds which were, well, they predicted this leading term. So they obtained this using a combination of two types of techniques. First they used rigidity properties of the Airy point process, and then also they used some knowledge about the spectrum of the stochastic Airy operator. So those are the techniques that they used, but as I understand it, those techniques do not allow to go beyond the leading term in the expansion. So then maybe the most interesting regime is the regime when this s times t minus 2/3 goes to some constant, a strictly positive constant, and then we obtain that we get this phi, which is really evaluated at a fixed point y then. And this, yeah, okay, it's not exactly correct as it is. I should say if st minus 2/3 is equal to y, then you have this value. Otherwise, the error term depends on the speed of convergence here. So it's a bit sloppy here. But in any case, this result, this leading term, was again known. This had been obtained also last year by Tsai, who also proved this using the spectrum of the stochastic Airy operator. They were predicted slightly earlier by Sazorov, Meyerson, Prolak, also by Kryenbrink, Ledoussal, Prolak, and Corwin Ghosal in combination with Kryenbrink, Ledoussal, Tsai. But all these results are very recent. These are not the publication years, they are the archive version years. Yes, so now indeed, going back to Alexander's question, letting y to infinity is not allowed, but we can formally just look at the result and let y to infinity. And if we do that, what we obtain is this cubic term, which is precisely the tail of the Tracy-Widom distribution. So everything looks consistent. And so we believe that, in fact, there's not really, as t goes to infinity, there's not really anything interesting happening there anymore. But there are technical problems that we cannot immediately resolve to have rigorous.
One more. So if you are on the boundary of your region, this all becomes bigger than logarithm square.
Yes.
So this is a two estimates which
Yeah. Now, in the error terms which we obtain, it's not so clear why or how these error terms will explode. Maybe they don't explode at all. I can't say much about what happens if we if we go to the boundary of this region. My feeling is that it's mostly a technical problem that we have, but okay. So small t, yeah, also an interesting question. I think I haven't told yet about the techniques. I believe that the techniques that we use, which will involve Riemann-Hilbert problems, they could also be used to study the t going to 0 limit. But indeed, t going to 0 is an interesting limit. There are some results known about the t going to 0 limit, but yes, in this limit, if you scale things, you approach, I believe, the Gumbel distribution. But yes, we didn't study that. There are also some technical problems which prevented us from doing it. But yeah. Okay. Yes. Okay. So now the second part of the talk, I will explain the methods that we use to prove these results. And so I already explained that what we need to analyze really is this function q of st, which can be written in two ways as a Fredholm determinant. Either this Fredholm determinant or this one with respect to this kernel coming from the models of finite temperature free fermions. Now, how can you analyze asymptotically a Fredholm determinant? So Fredholm determinant, you can, if you don't know anything about Fredholm determinant, you can take this as a defining property of the Fredholm determinant. It's this Fredholm series, which involves multiple integrals of determinants of the kernel. And just looking at this, if your operator k has a small norm, say trace class norm, then the asymptotic analysis here is easy, because this series in fact becomes an asymptotic series, in the sense that the first approximation will be 1 plus the, or minus the trace of k, and so every next term in this Fredholm series will be smaller than the previous one in the asymptotic limit. So in that case it's easy, and that's actually what happens if s goes to minus infinity. So this corresponds to the upper tail of the KPZ equation. That's a case that's easy to analyze, and standard operator estimates allow you to approximate the determinant. But now when s goes to infinity, this operator is not in any reasonable sense small, and then it's hard to compute asymptotics for Fredholm determinants. And the method that we use there is a method developed by Alexander Itz and Izergin, Korepin, Slavnov around 1990, which involves a Riemann-Hilbert representation for logarithmic derivatives of these determinants. And it works whenever the kernel is of a certain form, which is called integrable form. And it means that your kernel can be written as a scalar product of two vectors of functions divided by x minus y. And moreover, when the denominator vanishes, the numerator should also vanish, which gives this condition. Now, this method in principle works for any value of k. But then if you want to analyze this Riemann-Hilbert problem asymptotically, you would be happy if you have a value of k which is as low as possible. If k gets large, typically the asymptotic analysis of Riemann-Hilbert problems, which will then be of size k by k, will become complicated. And so if we look at this finite temperature representation of our function q, this is a kernel which is not really of this integrable form, but in fact you can approximate it by integrable kernels. You can discretize this integral, write it as a sum of kernels, and then using, instead of the integral version of the Airy kernel, the explicit representation for the Airy kernel, you can see that it's of integrable form, but with k going to infinity. So if you would apply this, this method, in this case it would lead you to a representation for logarithmic derivatives of the Fredholm determinants in terms of an operator-valued Riemann-Hilbert problem. There are some results by Alexander amongst others about asymptotic analysis for operator-valued Riemann-Hilbert problems, but nevertheless it's very hard asymptotically to analyze it. So this effect, this observation was made also by Amir, Corwin, Ghosal, that in principle this could lead to an operator-valued Riemann-Hilbert problem. But somehow, and I don't know why, but if you look, Amir, Corwin, and Ghosal were aware of this, this second representation also of the Fredholm determinant, written as a multiplication of two operators. But somehow they didn't try to apply the Itzizergin-Korepin-Slavnov method to this operator. Because if you do that, this is easily written in integrable form. Well, you can do it in many different ways, but for us this way is convenient. And so it's of integrable form with a value of k equal to 2, which means that it leads you to a 2 by 2 Riemann-Hilbert problem, and in such a case we know quite well how to study such Riemann-Hilbert problems. Okay, so the Riemann-Hilbert problem, you don't really have to memorize this. It's a Riemann-Hilbert problem on a contour in the complex plane, which is just the real line and the imaginary line, okay, with some orientation like this. And there are jumps on these two lines, there are jumps which are written here. And these jumps depend on this function sigma. There's a certain type of asymptotic behavior. And in these asymptotics, you may recognize the asymptotics of the Airy function. This is indeed exactly the same type of asymptotics as you have for the standard Airy function model Riemann-Hilbert problem. Okay, so this is a Riemann-Hilbert problem. The solution to it exists and is unique. And how does it relate to our function q st? Well, logarithmic derivatives with respect to s and t, or in fact with respect to any parameter on which sigma would depend, you can derive differential identities, and it can be written as this type of integral. Yes, so specific form here is not so important. This function psi hat is not exactly psi, it's some analytic continuation of psi. This is all not too important. The only thing that you need to remember is that if we have good asymptotics for psi, then we have good asymptotics for the logarithmic derivatives of these determinants. That's the only thing you have to remember from this. And now then the question is, how can we analyze this Riemann-Hilbert problem asymptotically? And so I'm glad that I'm, I think, the last speaker about Riemann-Hilbert problems, or one of the last, so that I can rely on all the talks that we've seen before. And so if you do a Riemann-Hilbert problem, you could say, why is this Riemann-Hilbert representation of the kernel interesting? Because in principle you start from a Fredholm determinant, which is a more or less explicit object, and you express it in terms of a very complicated thing, in terms of the solution of a Riemann-Hilbert problem. But like we saw yesterday in Ken McLaughlin's talk, you could think of the analogy with n factorial. If you want asymptotics for n factorial, Stirling approximation, you first need to write it as an integral, which is a priori a more complicated object than a factorial, and then you start working on this integral, and it's the same general idea here. So we now just look at this more complicated representation. We try to obtain asymptotics for psi, substitute that in these integrals, and this will give us asymptotics for log of q. Now, in such a Riemann-Hilbert analysis, there are various transformations one has to do. And one crucial thing in a Riemann-Hilbert analysis is typically the construction of a suitable G function. André Martinez-Finkelstein's talk of this morning was all about equilibrium measures, which are in a sense the same as asking construct a suitable G function to do the asymptotic analysis of these multiple orthogonal polynomials in this case. So here this is also an important question, which is a good G function we can use to do the asymptotic Riemann-Hilbert analysis. And the heuristic picture of this G function is that it's related to this density of the Airy process, which has this square root law. But now, so this for small t, we could construct the G function using this density. So you could think of this as an equilibrium measure out of which you can construct a G function. But for large t, this is not a good G function anymore, and there, instead of taking the density of the Airy point process, we need to take the density of the Airy point process, but conditioned on the event that the tint Airy point process, which we obtain by removing each particle independently with a given probability, conditioned on the event that this tint Airy point process is empty. For small values of t, this conditioned density will be roughly the same as the unconditioned density. But for large t, this changes. This conditioning really influences the typical configuration in the Airy point process. And so then we have a different density, I would call it, that we use to construct a G function. Okay, and so this density, the larger t, the more the particles are pushed to the left. So this, yeah. Okay, so these are the heuristics behind the construction of this G function. Here are some formulas which look horrible, but just to show you that we can construct these things explicitly. So psi, after a change of variables, it behaves like the square root. So this would just correspond to the unconditioned density. And then there's a second term, which becomes larger if t becomes larger, which is quite complicated, which also involves this function sigma. But okay, it's an explicit integral. What is lambda 0 here? Lambda 0 is the endpoint of this. So this is a density supported on minus infinity up to lambda 0. And the value of lambda 0, lambda 0 solves an explicit equation. And if you solve this equation for large s, the solution is this, up to small error terms. And now it's in the Riemann-Hilbert analysis, it's really analyzing this density and this endpoint and studying properties, analyticity properties of this density. That's really the hardest part in the Riemann-Hilbert analysis. And once we understand these functions sufficiently well, then we can use it to apply a more or less standard version of the steepest descent method for Riemann-Hilbert problems. The other ingredients we need in the Riemann-Hilbert analysis are the construction of a global parametrics, which is simple explicit formula, and of a local parametrics near this endpoint lambda 0, which is just an Airy parametrics, which is also fairly standard. And the results from this Riemann-Hilbert analysis is that we get asymptotics when s goes to infinity for t in this region. So the problem if t is bigger is that this endpoint lambda 0 will then go to 0. And 0 is a point that is not so pleasant because the function sigma, which was 1 over 1 plus exponential, this function has poles on the imaginary axis. And for large t, those poles, they will approach the point 0. And so the construction of this local parametrics will start to near 0 will start to interfere with the poles of this sigma. And that's the problem that appears if we go outside of this region.
What looks like a simple technical problem. I would expect
No, indeed, in terms of the Riemann-Hilbert problem, I also expect it's a hard problem. But in terms of the results, it seems that we don't have to expect a different result. But so in a way, you would expect that if t goes to infinity very rapidly, you would expect instead of an Airy parametrics, maybe rather a Bessel parametrics.
that's true, but
And to change from one to another, from the Riemann-Hilbert point of view, this is indeed, it looks very hard. But I suspect that the result, the theorem is, I suspect it's true also outside of this region. But how to prove it, that's a
verify you will get Claeys usually. But in between you might.
Yeah, true. Yeah. Okay. Yes, and so then from that point we just substitute the asymptotics for the logarithmic derivative in this identity. We have to work with those integrals. This is quite a long computation to get asymptotics for all those integrals. But this, after long calculations, this leads to the theorem. So there's one. Okay, I still have a couple of minutes. So there's one more thing that I would like to mention here. That is that these determinants Q of ST, they're also interesting from the point of view of integrable differential equations. And not only for this specific choice of sigma, you could now think of any function sigma which converges to 0 sufficiently rapidly at infinity and tending to some constant at plus infinity, and which should be sufficiently smooth. I don't know precisely for which class of functions this we're able to see now that it holds for a rather general class of functions sigma, but we didn't really define the broadest class we can find. But so there are two different observations. First, Amir, Corwin, Ghosal, they proved that these determinants, also for general sigma, they are related to an integral differential generalization of the second Panevet equation. So they used essentially Tracy and Widdom's method to derive this generalization of the Panevet-2 equation. We can now also see this from the Riemann-Hilbert problem. We can derive not really Lex pairs because we don't have an isomonodromic problem, but things which are somewhat generalized Lex pairs, and we can see from the compatibility conditions of these equations that indeed we get this integral differential Panevet-2 equation. What we can see in addition from this Riemann-Hilbert problem is that there is a connection also with the Korteweg-de Vries equation, KdV equation, which is the following. I will first state this result with corresponding to the integral differential P2. So the second log derivative of Q can be written as such an integral where this Q is a function of two variables, and as a function of S it satisfies this integral differential version of Panevet-2. So if this would just be Q squared, this integral, then it would be the standard P2, but now it's an integral, so it's and yes, it has this boundary behavior. So I think essentially nothing is known about solutions to this integral differential Panevet-2 equation. So then now the connection with KdV is the following. So we need to do a change of variables. So we need to set S equal to x times t minus 1/3. So now we have a little x and little t, which will be the KdV variables. And the capital T has to be 1 over t squared. We can write this as some function u of xt minus this explicit term. Well, if we write it in that way, then u solves the KdV equation, normalized in this way. I don't know what to say about the initial data of this KDV solution. It appears to be very complicated. We cannot compute the t going to 0 limit of this solution. We can do some formal computations, and we believe that some region of the real line, the t going to 0 limit is just infinity. Some other part of the real line, it appears to be something well defined, but we cannot really compute this limit rigorously. But it seems unlikely that this is a KDV solution which belongs to a class for which direct and inverse scattering methods are known. Sorry?
Recently we did it with Vladimir Sukhanov at this so-called cylindrical KDV equation. And so you consider KDV equation, so like square is with a so-called start operator. So initial values, they go to x to linear function.
Ah, yeah, okay. But you think this is related to this?
Yeah, I'm absolutely sure.
Okay.
We can discuss.
Ah, interesting. Okay, good. Okay. Yes. So there's not much more I can say about this KDV solution at this point. There's also recent work by Quastel, which appeared 1 or 2 weeks ago on the archive, which gives a relation between KPZ and the KP equation. Which, okay, if you just listen to the acronyms, this doesn't seem surprising, but there's no relation between K and P and KPZ and from KP. But there's a relation there. I don't think, if I understand it correctly, it's not exactly the same as this relation with KDV, but there's probably a relation between it, but I haven't been able to really understand how this works. But this is just to mention that also, yeah, there's some integrable structures behind that are not really understood at this point. Okay, that's all I wanted to say. So thank you very much. Yeah, so you mean this combination that appears? Yeah, it seems very well studied. Yeah, I don't know. So I think this is related to what is called KPZ scaling. So there are definitely good reasons why this combination precisely appears, but I'm not really able to tell you much more about it. Sorry?
I say 1/3 is everywhere.
1/3 and 2/3 are everywhere in these KPZ scalings. Yeah, that's true. Yeah.
Okay, please. How do you see the KDV equation coming out of that? Is it from the Riemann-Hilbert?
Yeah, it's no. So you have to just to do this change of variables from capital T and capital and S to X and T, and it becomes a.
Replace zeta by z plus f. Introduce new variable, and then your exponent would become KDV dispersion.
Yeah.
But square root of z.
But it's not just on the real line; it's on a contour. Two sets of contours.
No.
But
first of all, of course, we have to double check. But I'm almost quite sure that we can consider, because again we consider it completely different asymptotic question.
Mm-hmm. Okay.
But it is still. So there's the fact that it is related. That's why I said about star, because in the usual KDV, when everything decays, you construct direct scattering transform using that as a vacuum solution plus exponents. So this is how you define your reflection coefficient. So this. But now, if your potential approaches not 0 but x, then instead of the exponents, you will have Airy function. And so all your, your solutions, everything is defined on the background of the Airy function. And so in Riemann-Hilbert problem, instead of exponents, you will get exactly Airy function. So more or less, and this sigma, it plays the role, of course, of kind of reflection coefficient. And indeed, there is a problem with t equals 0. Absolutely, because you have to replace this x in initial data by x over 2t. X over 2t is a particular solution of KDV. So you have to start with t equals 1, for instance, actually. And when t goes to 0, it is a kind of separate asymptotic analysis to see what is going on.
The Fourier coefficients come from the asymptotics, either negative 2/3, say even a 3 times that.
Yeah. It is as usual. You have first, with your problem on the real axis with complicated jump matrix, Airy functions involved, and then you undress it. You just undress it, go explain the Airy function by the asymptotic. Any more? Yes.
KDV has several candidates of self-similar solutions. So do they use something interesting?
Yes. Is your question is probably something in the style? Is there a general? Is it true in general that solutions to this integral differential P2, for instance, they lead to solutions of KDV? So there's self-similar KDV solutions which relate to Panevet-2. I guess yes, in some limit you can get them from here. What's also interesting is that for it's a different property, but for this specific choice of sigma which appears in KPZ, this KDV solution appears to be quasi-periodic also. So there's some special property, but that's not true in general. Not for general sigma. But yes, I don't know anything else to say about the self-similar solution.